A piston cylinder device contains 0.85 kilogram of refrigerant 134A at negative 10 degrees C. Given mass of the refrigerant is given 0.85 kilogram and T1 is given negative 10 degrees C. The piston that is free to move has a mass of 12 kilogram and a diameter of 25 centimeter. So mass of the piston is given 12 kilogram and the diameter of piston is given 25 centimeters. So let's clarify, this is the mass of refrigerant. The local atmospheric pressure is 88 kilopascal. Pressure of atmosphere is 88 kilopascal. Now heat is transferred to refrigerant until the temperature is 15 degrees C. T2 is 15 degrees C. Determine the final pressure. We are interested in P2, the change in the volume of the cylinder, delta V, and the change in enthalpy of the refrigerant, delta H. I take the refrigerant in the cylinder as the system. It's a closed system because no mass crosses the boundary of the system. Then to solve for pressures, I can use the free body diagram of the piston, write down the equilibrium equation in the y-axis, and solve for the pressures. So for the initial state, this is going to be the free body diagram of the piston. For the free body diagram, I draw all the forces that are applying on the object. P1, or pressure of the refrigerant in the initial state, times cross-sectional area of the piston. Atmospheric pressure times the cross-sectional area of the piston. And the weight of the piston. So sum of forces in vertical direction is 0, or P1 equals atmospheric pressure plus the weight of the piston, which is mass of the piston times the gravitational constant divided by the area of the piston. Atmospheric pressure is given 88 kilopascal. Mass of the piston is given 12 kilogram. G is 9.81 meter per second squared. And area of the piston is pi divided by 4 times the diameter squared. Moving on to state number 2, I can draw the same free body diagram and I can write down the same equation because no additional force is applying on the piston. So P2 equals P1 equals atmospheric pressure plus the weight of the piston divided by the area of the piston, which is 90.4 kilopascal. And please make sure to check the units. So this is going to be our final pressure. Then moving on to delta V. Delta V is V2 minus V1, or M2 times the specific volume in state 2 minus M1 times the specific volume in state 1. And we are dealing with a closed system. Mass remains constant. Mass of the refrigerant is given 0.85 kilogram times V2 minus V1. So we just need to read a specific volume from the table. To do that, we need the states. State 1, temperature is given negative 10 degrees C, and we just solved for pressure. P1 is 90.4 kilopascal. And to determine the state, I can go, for example, to the pressure table. At the given pressure, I can read for T stat. It will be negative 28.65 degrees C. Then I can compare Tsat with the given temperature, which is negative 10 degrees C, and I see that the given temperature is greater than Tsat, or the state is superheated vapor. Then I can go to the superheated vapor table for refrigerant 134A and read for a specific volume. State 2, temperature is given 15 degrees C, and we solved for pressure. P2 is 90.4 kilopascal. Again, we need to determine the state. We already read for Tsat at 90.4 kilopascal. I'm going to rewrite that. Tsat at 90.4 kilopascal is negative 28.65 degrees C. Let's compare it again with T2, which is 15 degrees C. Again, T2 is greater than Tsat, so state 2 is also superheated vapor. We can go to the superheated vapor table one more time and read for a specific volume in the final state. So V1 is given, V2 is given. I can plug into the equation for delta V and solve for delta V. It will be 0.0205 meter cubed. Then for delta H is H2 minus H1, or constant mass times H2 minus H1 per mass. We know the state. We can go to the table. At the initial state, I can read for H1, and at the final state, I can read for H2. Plug them into the equation for delta H, and delta H will be 17.4 kilojoule.